plan for today. Today is class number 5. Lecture A. Actually, I'm going to start with something that's not on here. I finally got some Mathematica things to work, so I want to show you some of the demonstrations I've created to illustrate some concepts. You don't have to know this Mathematica stuff, but it illustrates some things in a nice way. It's not shown in there. I'm going to then move to that homework problem that you had, actually 2 homework problems about grading on a curve, and talk about how to do that actually with a spreadsheet as well. Then we talk in a lot of detail about correlation, how to compute it with a spreadsheet. You're going to have to compute it with a spreadsheet on your assignment. You're going to have an electronic portion to the next assignment. Regression. Yes, I'm talking about how to do those things with spreadsheets and calculators. Lecture B will be more about regression, more details, also discussing some regression pitfalls, some cautions, and a brief introduction to what are called sampling designs, which is the start of chapter 3. So I was excited. I finally got the computer working here to be able to, oops, how do I get rid of this here? There we go. To be able to look at some of these Mathematica demonstrations. For example, this is some code that will illustrate that the mean is the center of mass. This is for a data set rather than a density curve. You don't have to understand what this code is doing, okay? That's not the point. I have fun with it. The point is that it illustrates some things. I can use it to illustrate some things in this class kind of nicely. What I have here is a number line, and I have a bunch of dots in the number line representing numbers on the number line, representing data. And the blue arrow there is at the location of the mean. If this number line were a seesaw, and if these points, these data points, were masses of equal mass that you were putting on the seesaw, again, the mean is where the fulcrum, where to put the fulcrum to make it balance. Effectively, you have to imagine the seesaw is infinite here, and you have to imagine the seesaw itself has no mass. It's the center of mass. As I move the slider, I can change the location of one of the data points. That leftmost one is changing. Sometimes it equals some other data value, and when that happens, you can see it gets plotted on top of that other data value, but don't worry about that. I'm moving that over to the right, and that's affecting the mean. It's becoming an outlier about now. The mean is definitely sensitive to outliers, not resistant. It gets pulled to the right as that outlier moves to the right. You have to move the fulcrum to the right to make the seesaw balance. Okay, so a little fun I had with that. I also have a demonstration about normal curves. To really emphasize something, to really emphasize that the area under the normal curve, no matter what the mean and no matter what the standard deviation is, the area is always equal to 1. For example, this produces output that's the graph of 3 distinct normal curves. The red one is the standard normal curve. It's centered on the origin, 0. That's where the peak is. It's got a standard deviation of 1. This is 1 right here. If you go up to the red curve, that's the location of one of the inflection points. At -1, which is right here, that's the location of another inflection point. Graph is concave down between the inflection points, looks like a frown, and it's concave up to the right of this one, looks like part of a smile, and concave up to the left of that one, looks like part of a smile. The blue one is also got a mean of 0, but the standard deviation is bigger. I made the standard deviation equal to 3, actually. Here's 3, and there's one of the inflection points. Here's -3, there's another inflection point. The graph has to be lower to make the total area under it still equal to 1. And finally, the purplish-looking one, magenta actually, is got a mean of 3, and it's got a standard deviation of 2. 3 plus 2 is 5, there's one inflection point. 3 minus 2 is 1, there's another inflection point. And then this other code makes animations that allows me to change the mean and standard deviation. Changing the mean just shifts the graph left or right. Changing the standard deviation affects the spread and therefore also affects the height to make the total area always equal to 1. Okay? So that's something you should have in the back of your mind. It actually is relevant for solving some problems, especially in chapter 6, to realize this. Okay? It's something to keep in the back of your mind. I'll bring it up at an appropriate point later. let's look at that grading on a curve problem. Let's see, where is it? Oh, before I do that, I did have this slide here before, but I kind of jumped over it before. I don't want to jump over it today. Let's look at it briefly. You should know, for this class, the letter Z almost always represents a variable that is normally distributed with a mean of 0 and a standard deviation of 1. It's called the standard normal distribution, or the standard normal variable. I haven't emphasized this notation, but you've read about it in the book. If you write n0, 1, that's just shorthand. It's shorthand for representing a normal distribution with a mean of 0, that's the first number, and a standard deviation of 1, that's the second number. All it is just shorthand notation. Okay, you've seen it before in the reading. That's the first thing to note. We have talked about computing z-scores with this formula before. Let me emphasize that the original variable x, in order for this to be a true z-score in the sense of it being standard normal, x also has to be normal. It's not that you can't compute z-scores for non-normal distributions, and some people do and they still call them z-scores. However, the normal model wouldn't work then. You wouldn't want to use the table in the front of the book to calculate those percentages. Okay? You can still call it a z-score. It's still going to measure how many standard deviations you are away from the mean. That still will be true for non-normal. But in order for z to be truly modeled by a standard normal distribution, x itself has to be from a normal distribution. Here's your general kind of notation. N, mu, comma, sigma. That's just shorthand. It represents the normal distribution with a mean of mu and a standard deviation of sigma. Actually, let me just briefly say, you should be aware that statisticians actually use slightly different notation. They put the square of the sigma here, and they call it the variance. But it's going to be simpler for us to just call it the standard deviation. Don't square it. Okay? That'll be a simpler notation for us. You should know for future quizzes and, say, the first exam and later exams, you should know that z, this formula, does essentially count with a sign, positive or negative, and also possible non-integer values, how many standard deviation of data value is above or below mean. Positive z's, you're above mean, negative z's, you're below mean. If z is 1.7, that means that data value is 1.7 standard deviations above the mean. And a data value, a z value of negative 1.7 would tell you the data value is 1.7 standard deviations below the mean. This is stuff you should know. Let's think about it in the context now of that grading on a curve problem. Exercises 1.99 and 1.100 for those people still using this book in the future. We probably won't be. We're talking about exam scores. It's on page 61. For a course based, and the grades are assigned A, B, C, D, and F on a curve. First time I ever heard of grading on a curve was when I was in 6th grade. My 6th grade teacher sort of gave us a lecture like, when you get to junior high, we called it junior high back then, we called it middle school. When you get to junior high, your teacher's probably going to grade you on the curve, and it made it sound really scary. Actually, my teachers didn't grade me on a curve. And I don't know that I've ever had teachers grade me on a curve. It's actually a good thing if the class is really hard. If the tests are really hard, it's actually a good thing to be graded on a curve because it could be like getting 50 on a test could be an A. If the test is really hard, it could be a good thing. It's not such a good thing if the tests are really easy. In fact, my dad told me a story that he had a class where the professor graded on the curve, but the tests were really easy, and he got a 92 and he failed. Okay? People who got like a 97 got an A, 96 was a B, 95 was a C. You know, it was kind of crazy. The test was too easy. Okay? So it's not good to grade on a curve when the test is too easy. But anyway, in this problem, based on past data, this professor is assuming that the scores are normally distributed with a mean of 70 and a standard deviation of 10. If you're going to draw a picture for that, which I think is a good idea, draw a normal curve centered on 70 with a standard deviation of 10. There is the inflection point above the mean. This would be an 80 right there. Here's the inflection point below the mean. This would be a 60. So that's a curve that's going to model histogram of past data pretty well. That's the idea. The lower boundaries for the various grades are based on percentiles. I should probably add that these are percentiles before I put this on Moodle. Okay? To get an A, you got to be at the 85th percentile or higher. To get a B, you got to be at the 55th percentile and below the 85th. To get a C, you got to be at the 15th percentile and be up and be below the 55th. And to get a D, you got to be above the 5th and below the 15th. And then people below the 5th fail the test or the class. Are these boundaries that everybody uses? Not necessarily. Not all professors use these as boundaries if they do grade paper. They might choose different ones. They might choose it to be more symmetric for one thing. Anyway, let's try to guess where these boundaries are. I mean, you figured them out. You were supposed to figure them out for your problem. Let's try to guess where they are based on the 68, 95, 99.7 rule. So listen real carefully. Again, 68% of the data are going to be within one standard deviation of the mean. In other words, between 60 and 80. And again, we're not worried here about whether it's inclusive or exclusive. Is 60 and 80, are they included in that or not? Okay, it does actually make a difference for this type of problem where your data are discrete, whole numbers, for example. But we're not worried about that extra complication right now. Don't worry about it, is the main point. So we're going to say essentially 68% of the data from past exams, scores are between 60 and 80. Not worrying about inclusive or exclusive. What does that leave? That leaves 32% for the extremes. And by symmetry, it's got to be divided by 2. 32 divided by 2 is 16. You're going to have 16% over here and 16% over here. I guess I'm just thinking about the 68% right at the moment at least, not the 95 and the 99.7. What does that mean, for example, about a score of 80? What percentile rank is that? Just find the area to the left of 80, which is going to be the sum of 68 and 16, 84. 80 is about the 84th percentile, which is very close to the lower boundary of the A. The 85th percentile score is going to be a little bit above 80. Maybe it'll even round to 80. Might round to 80, might round to 81. Let me just mark that as the 85th percentile score. It's really a score. It could round to 80. Okay? B is at the 55th. What number on the number line has 55% of the area to the left of it? Well, 70 has 50%, so it's got to be bigger than 70. How much bigger, I'm not sure. Maybe 71 or 72. Just a guess. This is at about the 55th percentile score. The lower boundary for a B. 15th, that's 16% of the area. 15 has got to be just lower than that. Might even round to 60. Could round to 59, I don't know. That's the 15th percentile score. And then the F, or the lower boundary of the D, is at the 5th percentile. Where is that? Well, now if you think about the 95% for 2 standard deviations away from the mean, I'm just going to think about it visually here, not draw it. Think with me, 95% of the data approximately was within 2 standard deviations of the mean, between 50 and 90, leaving 5% for the extremes past those and 2.5 on either side. 50 is 2 standard deviations below the mean, so 2.5% of the data would be over here, corresponding to 2.5% of the area. You want 5% of the area, it's going to be bigger than 50, maybe about 52. That's approximately the 5th percentile score. So what I'm trying to advocate here is if you make drawings like this and think carefully, you can figure out approximately what the answers are going to be before you ever even do any calculations. That's a very good thing. That helps you know what to expect. Helps you guess and see whether you might be wrong. Okay? Let's get into details of some calculations here, though. I put these in a spreadsheet, and I'll share these with you. So these were the numbers that were in the problem. These were the scores of the latest class. 68, 54, 92, 75, 73, 98, 64, 55, 80, and 70. Okay? based on those, I could look at this picture and try to estimate who got A's, B's, C's, D's, and F's. For example, the person who got 68, right there, looks like they got a C. 55, that's the B boundary. We're not worried about C pluses or B minuses here. Person who got a 54, probably they got a D. Person who got a 92, they got an A for sure. 75, probably a B, looks like. Okay? Again, you can get expectations from this. It's a good idea to answer this definitively by converting these to z-scores and using table A. That's what you should have done. Find the z-score percentiles in table A that correspond to these numbers from the data. Here's a way you can convert these to z-scores with a formula. The mean is 70, the standard deviation is 10. I can just do that. Take a look at that, zoom in on it. With the formula I did equals B6, which is the 68 for this first data point, minus the mean, which was 70, divided by 10. By the way, the mean of 70 and standard deviation of 10 is not the mean and standard deviation of these data. It's the mean and standard deviation of past data from maybe hundreds of students who've taken it in the past. So that's going to compute 68 minus 70, which is negative 2. You divide that by 10, you're going to get negative 0.2 for this one. And you can copy and paste that downward to get the other z-scores. Notice that a z-score of 70 gives you, an actual score of 70 gives you a z-score of 0. That's the mean in the past data. What did you need to do? You should have used table A. Which is right here. I've also got a link to a website with table A, and actually another table that we need today. For example, to find the B line, let's focus on the B line. 55th percentile, you need to look for the area here closest to 0.55. Using this backwards, like I mentioned on the assignment. Look for the area that's closest to 0.55. These are the two areas closest. That one's a little closer than this one, 0.17 away instead of 0.22. So your best approximation here for z is 0.13. Probably a better approximation is 0.126 or 0.127. But you should have gone ahead and used 0.13 as your z-score that's at the 55th percentile, the lower boundary for a b. And then, to find the corresponding lower boundary for the actual scores, use the z-score formula in reverse. Remember, we solved it for x before. Multiply both sides by sigma and then add mu to both sides. X is mu plus sigma times z. So when z is 0.13, this becomes 70 plus 10 times 0.13. That's 1.3. You get 71.3, approximately 71 as the lower boundary for the b. And that matches our expectations. I said maybe 71 or 72. Okay? And then that helps you in the data to identify who gets a b. If the professor is feeling generous, I suppose he or she rounds the b line down to 71. If they're feeling not so generous, maybe they round it up to 72. Okay? It kind of depends on what the professor feels like doing. Do I round things, your scores up or down? Okay? I think I did mention it, maybe I didn't mention it in this class. If you're close to a boundary, okay, I might round you up, but what I want to see is I want to see evidence that you've gone to math lab for one thing. So make sure if you go to math lab that you sign in and sign out, and or coming to office hours. And actually, it's so far only one person has come to office hours in this group, so that's something to consider doing here. Okay, any questions? Can I clarify anything? I'm not going to bother with the other lines because it'll take too much time here. But you get the idea? Okay. So that would be how the professor grades on the curve. If the mean and standard deviation were different, the percentiles would still be the same, but the boundaries would be different. The mean and standard deviation are different. The corresponding z-scores would be the same. All right, on back to scatterplots, regression, and correlation and regression. Very quickly, let me remind you, philosophically speaking, it's important when you're first trying to look at a relationship between two data values, two variables I should say, x and y, that you first make a graph. Okay? Don't start by doing computation. You want to first make an accurate graph, make sure it's accurate, to give yourself some visual understanding of what's going on and to set your expectations, just like I set expectations here. You do need to make sure the graph is accurate, but once you are confident that the graph is accurate, then by making the graph, that helps you set expectations. It helps you know whether you should even use correlation and regression in the first place, actually. Okay? Like for highly nonlinear data, you shouldn't use correlation and linear regression. All right? So make a graph first, and then look for the describing the graph by its form. Is it a linear trend? Is it a nonlinear trend? It could look like a curve, or it could look like a sine wave, maybe. That could happen. That's the form. What's the direction? Is it an upward trend or a downward trend, or both if it goes up and down? Go down and up. How strong is it? Is it a moderately strong / weak one like this one, or is it very close to being on a straight line or close to being on a curve? That's a strong relationship. And look for outliers. Okay? Either as mistakes or as important things to take note of. I got these graphs on here still, but I'm not going to talk about them for the moment, at least not today. I might come back to this one maybe next class period. Here's the formula for correlation. Okay, so again, write this down if you haven't yet. It's the formula in our book. I will re-emphasize once again that it's not the main formula that people use when they do correlation. In fact, when people do correlation in real life, they almost always use a computer, spreadsheet, software, or a calculator. Okay? They almost never calculate correlation with this formula. Why is it in the book? And why am I going to give you a problem, an electronic problem for next time where you actually have to use this formula? The reason is it can help you get a basic feel for why positive trends give you positive correlations and negative trends give you negative correlations. That's the main reason. It's worth using once at least. You're not going to have to do it by hand. You're going to use a spreadsheet in a way I'm going to show you in a minute. Okay? So again, that's pretty much the only purpose. Well, practice with the spreadsheet is another purpose. So, two purposes for us. Get a feel for why the correlation is positive or negative, and more practice with the spreadsheet. Okay? It's not really a formula that's used in practice. There are other formulas. If you have used formulas, there are other formulas that are used more often. Got that down? I'll go back to it. Well, maybe I should put it on the board since I'm going to go to the spreadsheet. I'll write it in the sloppy way without putting the index of summation here, just because it's a little quicker to write. You should put subscripts on the s's, though, to emphasize s sub x is the standard deviation of the x's, and s sub y is the standard deviation of the y's. That is important. Put there. All right, so I'm going to go back now and compute this correlation with the formula. You'll have a problem like this. And let's go ahead and do it for some data I gathered this morning. For fun, some baseball data. Joe Mauer. What is this data about? These are Joe Mauer's averages and home runs in seasons with at least 500 at-bats. Okay? These years, notice that 2007 and 2011 are missing because he had fewer than 500 at-bats those years, probably because he was injured. Batting averages and home runs. I did make a scatter plot over here of these data. And I included in the scatter plot the regression line over here and the square of the correlation. The quickest way to find the actual correlation without the formula in the book is to use the built-in function equals correl. You did this for the assignment, right? I told you how to do it in the directions. Highlight the x values and the y values and put a comma between them, and actually it tells you here the syntax would be the y values first and the x values, but it actually doesn't matter. For some reason it's assuming my y values, okay, it's assuming my y values come before my x values. I'm actually doing B5, those are my averages, through B13. It's hidden here. Those are my averages. Jerome Hour's averages, I should say, comma, C5 through C13. I don't know why it's not letting me just highlight it. Okay, I guess I gotta go over here. C5 through C13. In this graph over here, again, I put the squared correlation, which was about 0.6 there, r squared. The square root of 0.6 is what? Approximately almost 0.8. Is it a positive correlation? You can see in the scatter plot it does look like it's an upward trend, and I added the trend line. It's got a positive slope. It will be a positive correlation, a little less than 0.8. 0.773578. Now we want to use the formula to calculate this. However, if you look at this formula, you need some other statistics. You need the mean of the x's, the mean of the y's, the standard deviation of the x's, and the standard deviation of the y's. All right? Well, that means you need those. You're going to have to compute them somehow. Why not compute those with built-in functions? Means, standard deviations, equals average. We'll compute the mean. So first we'll compute the mean of his batting averages, an average of averages, that's okay. I can click and drag that formula to the right. And it will go correctly, even though I'm not using dollar signs, because it's just focused in column B. It will get switched to column C when I click and drag it to the right. And then I can do the standard deviations, equals STDEV, B5 through B13 again. Click and drag that to the right. Okay? There we go. How can I use these numbers? I want to use this formula. I want to get practice confirming the correlation is correct with this formula. Watch carefully here and think. You've essentially got products of kind of like z-scores. This is like x minus mu over sigma, except it's z-scores for data rather than a density curve. Standardized versions of x and y values. I'll label these columns standardized x's and standardized y's. I'm also going to have to multiply those before I add. Think carefully about the order of operations in the formula is another good thing to practice with formulas. I need to find the products of those. Okay, so you're going to want to structure your table for your electronic assignment in the same kind of way. How can I do this with the formula? Okay, standardized x's. I think I better use parentheses here because I'm going to do a subtraction on top. And I want to do the subtraction before the division. That's the way you do this, subtraction before division. I want to take the x value here in row 5 minus the mean of the x's, x bar, which is in B16, but I want that to stay fixed as I copy and paste, as I click and drag. So now I need to use the dollar signs to keep that cell reference fixed. $B, $16. And then divide by the standard deviation of the x's, $B, $17. Actually, it's sufficient to just have dollar signs in front of the b's here to keep the column fixed. Well, okay. In front of the numbers, actually. The column would automatically stay fixed. Okay, I was thinking about copying and pasting for the y's. Let's just do it this way. Let's not worry about whether we're keeping the column fixed or the row fixed. Use $2 signs in the way that I'm doing it. Okay, let's not worry about extra complications here. You do see the answer already, negative 0.73668. That is what you get. You can click and drag this downward. Now do the same thing for the y's, the home runs. Like that. Take a look at that. C5 is where that first home run total from 2005 is, 9 home runs in 2005. C16 is where the mean of his home runs per season is. Use dollar signs to keep it fixed. C17 is where the standard deviation is. Use dollar signs to keep it fixed. Copy and paste, click and drag it down. Like this. I'm now going to figure out the products. D5 times E5, the corresponding standardized x's times the corresponding standardized y's. Before I do this, I want to think about what's going to happen. There's the key. Will this correlation be positive or negative? I know the answer already is positive, but let's pretend we don't. What happens when you multiply two negative numbers? You get a positive number. When you multiply two positive numbers, you get a positive number. When you multiply a negative times a positive, like here times here, here times here, here times here, here times here, you get a negative. So the products of negatives times negatives and positives times positives contribute positively to the correlation, and the products of positives times negatives, or negatives times positive, contribute negatively to the correlation value. Which ones win out? We have to add those products up to see. But do notice here that that one's negative. As I mentioned, it would be. This, whoops, that's not good. This one's negative, as I mentioned, it would be, etc. There are 4 negatives and 5 positives, but more importantly, the positives are further away from 0 than the negatives are. When you add these up, do a sum now. You can use equals sum.